Alright, thanks for watching, and today I want to talk about an important topic called the continuous extension of a function. And by the way, if you're in my class, this is the only extension I will accept on an assignment. Anyway, so let me motivate this by an example. So consider the following function. So let f of x be x sine of 1 over x on the interval 0, 1. And very important, we exclude 0 because f is not defined at 0. So in particular, what this function looks like, well, it starts at 1 and then oscillates like sine, but oscillates quicker and quicker and quicker until you get this point 0 at which f is undefined. And here's the main question. Is there any way of defining f at 0 such that the resulting function becomes continuous at 0? Well, yes. Just define it to be 0 at 0. More precisely, consider the following. So let f squiggle be a function from 0 to 1 to r. Okay. Be the following. Be defined by f squiggle of x if x is non-zero. So on the original interval, it just becomes a function x sine of 1 over x. So on 0, 1. And moreover, f squiggled at 0 is 0. So 0 if x equals 0. So what this looks like, well, on our interval 0, 1, it looks like our function f. So this is f squiggled. And moreover, f squiggled of 0 equals 0. Now, what can we say about f squiggled? Well, first of all, on the original interval, 0, 1, it equals f. Okay? So it's kind of an extension of f on 0, 1. But moreover, f squiggled is continuous on the whole interval 0, 1. And this is what we call a continuous extension. So f squiggle is a continuous extension of f on 0, 1. In other words, a function that's defined on a bigger interval that agrees with f on the original interval and that is continuous everywhere, wherever it's defined. So here's a formal definition. So definition, so let A be a subset of B. So in our original problem, think A is 0, 1 and B is 0, 1. So think B as in bigger, so it's a bigger interval, and f goes from the smaller interval to r is continuous. Then the new function f squiggle from the bigger interval to r f squiggled from b to r is a continuous extension of f is on the bigger interval if two things hold. First of all, continuous, so f squiggle is continuous on b, and f squiggled equals f on the original interval on a. So again, what do we have going on? So we have, again, we start with f on some set A. Okay. And we want to define a continuous extension on a bigger set. Then all this means is the following. It's a continuous function on the bigger set that agrees with f on the smaller set. So you see, on the smaller set A, f squiggled is just f, so it's an extension, but think like extension cord, for instance, but f squiggled itself is continuous. So it's a continuous extension. Now let's look at example 2. Now let f of x be just sine of 1 over x, but on, again, our first interval 0, 1. So what this function looks like, well, it's like sine, but it oscillates wildly. Like that. Okay? So that's sine of 1 over x. And the question is, does this function sine of 1 over x have a continuous extension on the whole interval 0, 1? In other words, can we define the function at 0 to be something in such a way that the resulting function is continuous? And well, the answer is no, because look, remember, continuous means for any sequence converging to 0, f of that sequence converges to 0. But f of that sequence goes to f of 0. But here's the thing. Consider now this sequence of points whose value is 0 and that converges to 0. Then f of that value is 0, so f squiggled of 0 should be 0. Otherwise, we would have a different limit in some sense. On the other hand, consider the following sequence, where the value of the function is 1. Then, well, this sequence converges to 0, but f of that sequence converges to 1. So if f were continuous, the value of that function should be 1. And then we have a contradiction. It can't be 0 and 1 at the same time. This is not multi-track drifting. So here, f does not have a continuous extension. Continuous extension on 0, 1. In other words, there's no way of defining f at 0 in such a way that the bigger function is continuous. And therefore, we have two examples, right? We had the example of x sine of 1 over x that did have a continuous extension, and we have sine of 1 over x that does not have a continuous extension. And you're probably like, weird. What's the difference between the two? It turns out the main difference is uniform continuity, because, namely, this has a continuous extension because it is uniformly continuous, and this does not have a continuous extension because this is not uniformly continuous. And that's the main thing we want to show today. Now, let's show the following fact. Fact 1. Okay. So suppose you have a continuous function f from an open interval a, b to r, and this is continuous. So suppose you have a continuous function here, and f has a continuous extension. F squiggled from ab to r. Then it turns out f must be uniformly continuous. Is uniformly continuous on a comma b. So in other words, what is going on? Suppose you have a function f on the open interval a, b, and you can extend f to the whole interval. So this has a continuous extension f squiggle. Then it turns out that f must be uniformly continuous. And I will prove this in a second. It's super quick, but I do want to mention there's a lot of flexibility here. This also works for half open intervals and even for closed intervals. However, not for infinite intervals, because what makes this proof work is that this is compact. So here the closed interval a comma b is very important. And as an illustration, why is this awesome? Because this allows us to prove easily that the function is uniformly continuous. So let's go back to example 1. So f of x equals x sine of 1 over x on the interval 0, 1. Right? Then f is continuous on that interval and has a continuous extension. Has a continuous extension f squiggled on the closed interval 0, 1. Again, we've shown this kind of before, and therefore f must be uniformly continuous on the original interval. So if you can extend the function, then it's uniformly continuous. And let me prove that. The proof super quick, as I said. So suppose f, which is continuous, has a continuous extension f squiggled from AB to R. Okay. Then the point is f squiggled by definition is continuous, and it's continuous on this compact set. So then f squiggled is continuous by definition again on a comma b, which is compact. So by the previous video, one of the previous videos, we get f squiggled is uniformly continuous on AB. But you see, since it's uniformly continuous on the big interval a comma b, it must also be uniformly continuous on the smaller interval a comma b, so the open one. So f squiggled is uniformly continuous on a comma b, again, since this is smaller, but remember, on the smaller interval, f squiggled is just f. And therefore, f is uniformly continuous on a comma b. All right, and now let's show the second part. So fact 2. So if f from the open interval AB to R is uniformly continuous on AB, then f has a continuous extension f squiggled from the closed interval AB to R. Okay. So in other words, if you have a uniformly continuous function, like here, f on the open interval a comma b, then you can find a continuous extension f squiggled. Okay. And in fact, this can be used to show that functions are not uniformly continuous. Because consider the following. Again, our example 2. F of x equals sine of 1 over x on the interval 0, 1. We've shown before that this does not have a continuous extension. A continuous extension to 0, 1. I guess on 0, 1. And therefore, f cannot be uniformly continuous by the contrapositive of this. So f is not uniformly continuous. And by the way, try showing this directly. It's quite painful, in my opinion. So again, if it's uniformly continuous, then we can extend it. And now let me prove this, and the proof you'll see it's absolutely beautiful and super interesting. So proof. Again, step 1. suppose, again, you have a function f from a comma b to r that is uniformly continuous. And our goal is we want to find f squiggled. F squiggled from a to b to r. So again, what do we have? So this is f on the interval a comma b. And our goal is we just want to extend f to the closed interval a comma b. And here's the thing. So on the original interval, we can just define f squiggled to be f, which is continuous. So that's not a problem, which means we only have to focus on the endpoints. So what we want to do essentially is to define f squiggled here and f squiggled here and show that it's continuous. Now here's the thing, the case for B is entirely similar to the case of A, so let's just focus on the A part. And therefore, all we need to show is the following. So goal, again, new goal, we want to find f squiggled of A and show f squiggled is continuous at A. That's all. We just need to find one point and then we're done. Now, you'll see, as I said, this is a beautiful proof because we'll do a proof by wishful thinking. Okay? We really want f squiggle to have that property, and then we'll see it turns out it will have that property. Here's the main idea. And you're like, this is too crazy to be true, but it is crazy and it is true. So, idea. If with a big I, okay, f squiggled were continuous at A, then what would that mean? It means for any sequence converging to A, f squiggled of that sequence goes to f squiggled of A. Then, for any sequence Sn, let's say in the open interval a, b, if, or in other words, Sn converging to A implies f squiggled of Sn converges to f squiggled of A. But since Sn is in the open interval a comma b, f squiggled is just f. So in other words, we have f of Sn goes to f squiggled of A. So again, if it were continuous, this would be true. And here's the cool thing, proof by wishful thinking, define f squiggled of A as the limit of f of Sn, where Sn is any sequence in AB converging to A. So I know it's quite a mouthful, but let me explain. So now define f squiggled of A to be the limit as n goes to infinity of f of Sn, where Sn is any sequence in A comma B converging to A. In other words, again, let me illustrate with this picture. So we have, again, our interval a comma b. We have our function f. Okay? And the question is, how would we extend it to be defined at A? Well, this is saying all you need to do is take a sequence Sn that converges to A. Then, turns out, we will see, f of Sn converges to some limit, and it's that limit that we call f squiggled of A. Okay. All right. right? Of course, though, this raises two questions, because you're like, this is too crazy. Two things. I don't know if you realize, but of course, I don't know if you see it, maybe not, but this raises two important questions. First of all, how do we know this limit even exists? It could just diverge. And most importantly, how do we know it's independent of the sequence that we chose? Well, this we have to answer, and that's where we use the uniform continuity. So again, we need to show two things. First, that the limit exists and that it's independent of the sequence we chose. So if we're on step 2, claim number 1, if Sn is a sequence in A comma B that converges, in this case to A, then f of Sn converges. Because then the notation limit n goes to infinity of that makes sense. All right? So how do we prove this? Actually very quick. Okay? So suppose Sn converges. Okay? Then, in particular, Sn is Cauchy. But then by the previous video, we get that f of Sn is Cauchy. So that's the important thing about uniform continuity. It takes Cauchy sequences to Cauchy sequences. So because f is uniformly continuous on AB, and therefore, because it's Cauchy, it converges. So you see, the point is, in the real numbers, Cauchy is the same thing as convergence because it's complete. All right, now most importantly, let's show the elephant in the room, which is that. Now, most importantly, let's show the elephant in the room, which is that it's independent of the sequence that you choose. So step 3, I believe. Claim number 2. Namely, if Sn and Tn are two sequences in A comma B that converge to A, then the limits of f of Sn and the limits of f of Tn are the same. Then limit as n goes to infinity of f of Sn equals to the limit as n goes to infinity of f of Tn. All right, and it's just this amazing proof, if you want. So we have those two sequences, S1, S2, S3, etc., T1, T2, T3, etc., etc. How about we just interlace them? So let UN be just the sequence S1, T1, S2, T2, S3, T3, dot, dot, dot. Now here's the thing. Well, I mean, we can't show this, and I think the proof is in the notes, but the point is Sn goes to A, Tn goes to A, so if you interlace them, that should also go to A, because you see each term gets closer and closer to A. Then Un goes to A, and you'll see this is a lot of fun because we'll do f of Un. Fun. But then the point is, so then f of Un converges. F of Un converges. That's by step 1. I mean, that's by claim 1. And just careful, we can't say it converges to f of a because we don't know if f of a is defined. So let's say it converges to S. But here's the thing. So we have this sequence f of un. Okay, so this one converges to S. However, what is f of un? That's f of S1, f of T1. But f of un, by definition, it's f of S1, f of T1, f of S2, f of T2, So we know this whole sequence converges to some S. But then in particular, any subsequence should also converge to S. Then any subsequence converges to S. But then in particular, take the subsequence consisting of all the odd terms. Well, that's just f of Sn. So f of Sn must converge to S. On the other hand, well, now take all the even terms, and you get that f of Tn must also converge to S. And f of Tn converges to S, and therefore they converge to the same limit. So the limit as n goes to infinity of f of Sn must equal to the limit as n goes to infinity of f of Tn. And from now on, we can really assume that this weird definition is legit, because we know the limit exists and it doesn't depend on the sequence that you chose. And so finally, we can conclude. All right, and last step, and you'll see this is the most fun part. Let's show that f squiggled is continuous at A. So step 4. Show f squiggled continuous at A. Okay. But this is again a lot of fun, because suppose, well, Sn is a sequence in A comma B converging to A. Okay. And what we want to show that f squiggled of Sn goes to f squiggled of A. Now here's the thing. Well, we want our sequence to converge to A, so in particular it is closer to A than to B. So assume first of all that the sequence is not equal to B. It's definitely less than B, not a problem at all. For instance, if you have the interval 2, 3, then if Sn converges to 2, then it's definitely less than 3 at some point. And also, if Sn equals A, then we're kind of done. Then, f of S squiggle of Sn is f squiggle of A already. So, in particular, it's okay to assume that Sn is in the open interval A comma B. So without loss of generality, assume Sn is in A comma B for all n. And therefore, what is the limit as n goes to infinity of f squiggled of Sn? Well, since Sn is in A comma B, this is the limit as n goes to infinity of f of Sn. But remember, what was f squiggled of A? By definition, that was the limit of f of Sn. So by wishful thinking, we actually get that f squiggled of Sn goes to f of A, and therefore we're done. We've shown that f squiggled of Sn goes to the stuff that we want. All right, thank you very much.